Our present understanding of why deserts occur where they do is quite wrong. And the basic error goes right back to this familiar model, because geographers, even physicists, have failed to draw the proper conclusions from this standard laboratory experiment. You'll all remember what happens. The water will evaporate into the atmosphere. This is a closed vessel, until the atmosphere has become saturated, and then no further evaporation will take place. As soon as the atmosphere becomes saturated, and therefore no further evaporation can take place, it follows that the surface of the water will remain the same, and that's called the equilibrium level. That's what happens in the laboratory, and it's repeatable, and it happens presumably that way anywhere in the universe. Any laboratory in the universe. But what about the real world? Let's scale it up and look at the ocean and the atmosphere. Now, the atmosphere and the ocean are essentially a closed system. So the water level, is it going to go up or is it going to go down? Actually, it's behaving very oddly indeed. This system as a whole has had about 4,000 million years to reach maturity. So whatever is going to happen has already happened. And what has happened? Well, blow me down. After 4,000 million years, the atmosphere still is not saturated. And look, the sea level is in equilibrium. It may go up or down for other reasons, but when it comes to everyday common or garden evaporation, the sea level just stubbornly refuses to move. So it would appear that the physical laws are broken down completely. Now of course, orthodoxy has an explanation for all this, but we, at this stage, we're entitled to have another explanation, which is that the laws of physics pertaining to evaporation on a large scale, they're a bunch of horse manure. They're just plain wrong. We're entitled to assume that for the purposes of these proceedings. Look, we can't prove the proposition, but we're going to do the next best thing by demonstrating with repeated example, by constantly repeated experiments, as the phrase has it, that apparently the physical laws of evaporation do not apply in the real world of the ocean and the atmosphere. Let's be even bolder. Since sea level is at equilibrium, and since we know that equilibrium represents the position where evaporation no longer takes place, we'll take the situation at its face value and make this claim, this very stark claim. In normal circumstances, no evaporation takes place over the ocean. Which means, well, it must mean, in normal circumstances, rain does not come from the ocean. That's our claim. And remember, the facts, such as they are, so far seem to support us rather than orthodoxy. But let's run a test. Them against us. Orthodoxy says water is constantly evaporating from the ocean into the atmosphere. We say water cannot evaporate from the ocean into the atmosphere. One of us has got to be wrong. We'll pit our model against their model and see who wins. How should we conduct these trials? Well, one of the most important facts about weather systems is that they have a very definite tendency to travel west to east. It's because the Earth turns from west to east. So there's nothing surprising there. This being so, we can set up our experiment by finding a nice long stretch of west to east ocean. And since we know that weather systems will be crossing this ocean, if orthodoxy is correct, they will be picking up huge amounts of water via evaporation. And then these huge weather systems, with all that water vapour on board, they'll eventually hit land. And if we can arrange for, let's say, a nice mountain range to be right on that coast where it hits the land, then the clouds, the water vapour, will go straight up. And as they go up, they'll lose temperature, 3 degrees every 1,000 feet. And as clouds get colder, they can't hold as much water vapour, so they shed it as rain. So let's go for broke by finding the longest stretch of ocean in the world, which is here in the southern Pacific. And rather fortunately, we've got the Andes Mountains. Here they are. So let's see. If orthodoxy is correct, the atmospheric air mass that's travelling eastward across the Pacific, it'll have picked up vast amounts of water via evaporation, and then as soon as it hits land, it starts rising because of the Andes Mountains, it'll just start bucketing down. The Andes Mountains, they're 20,000 feet high, so the clouds will lose 60 degrees Fahrenheit. They'll lose virtually every drop of their water vapour. So the whole of this side of the Andes, well, it'll be sopping wet, if orthodoxy is right. Our own version is the exact opposite. Our rule says that as the air mass crosses the Pacific Ocean, it cannot acquire any water because we say that no evaporation ever takes place over the ocean. And so, therefore, we say this air mass will arrive at South America absolutely bone dry. It won't have a drop of water vapour in the clouds. In fact, there won't be any clouds. So, what's the result? What's the result of this first great trial of strength between orthodoxy and ourselves? Well, this area from the coast right to the top of the Andes, it's the Atacama Desert. It's not just the Atacama Desert. There are places here where there's been no recorded rain for the whole of history. It's never ever rained. Imagine. Orthodoxy says it should be bucketing down. We say it should be bone dry, and it's never rained. It becomes obvious that our model is likely to turn out rather better than the orthodox one. We can test it simply by showing in the real world the relationship between the world's deserts and the world's oceans, which is like this. Every desert in the world, apart from the special cases of the Gobi and Antarctica, every single desert lies at the eastern end of an ocean. Clearly, if rain was being generated in the oceans, and if weather systems were typically travelling from west to east, then it would be supremely unlikely that any desert would lie at the eastern end of an ocean. You might, by some kind of intellectual jiggery-pokery, account for the odd one, but for all of them to be exactly where they ought not to be, well, it rather suggests that the basic assumption is wrong. But now, this brings a problem for us. If the oceans are not the start of the hydrological cycle, which we seem to have discovered they're not, our own hydrological cycle will need to explain where the rain comes from. What is the primary cause of rain if it's not the oceans? Well, there's only one other candidate, and that's plants. Just as the ocean is supposed to produce water vapour via evaporation, so plants are supposed to produce water vapour via transpiration. Now, you might be concerned that the vegetable kingdom is it's somewhat puny compared to the vast oceans. But remember what Sherlock Holmes said. He said, once you've eliminated everything else, what's left must be the cause. But anyway, you're not being asked to believe this. At this stage, you're only being asked to open your mind and say, okay, what he said so far makes sense, so we'll go along with it, for now. So using our west to east model, we can begin to describe the way the true hydrological cycle works. Let's start here in London. Actually, London doesn't have a particularly high rainfall, nowhere near as Nowhere near as high as you might imagine from the constant moans of Londoners. But anyway, how can we predict with our new hydrological cycle that London isn't in fact a desert? This is how we do it. You draw a line due west from London all the way round to the opposite side of the world, which will be somewhere near the Aleutian Islands. Then all you do is trace your finger along this line and count the plants. Now, this is a rather odd concept, but anyway, let's just count the plants that happen to lie along this line. Here we have the first part. We've got across southern England. There's a whole bunch of plants in southern England, and they're all pulsating out water vapour like mad. Okay, it's mainly wheat fields and heathland and golf clubs, so not a huge amount of water, but still they're transpiring water vapour in fair amounts. Now we follow the line a bit further and it crosses the Atlantic Ocean. And we know the Atlantic Ocean produces nothing in the way of water vapour. But now we come to Canada. Hey ho, the line runs all the way across Canada. We've got several thousand miles of Canada with its coast-to-coast plants. And we're not now talking about, grassland and heaths and golf clubs. We're talking about trees. And trees gush out water vapour in prodigious amounts. Then we come to the Pacific Ocean, and that's it. Now, how many plants to supply London with rain? Well, that's the beauty of the system. If we think in terms of the turning of the Earth, and each separate line it's both gathering and delivering its bounty to every point on that line, then we have plenty of water for our purposes. So it's raining and it's gathering water and it's transpiring all the way across. Orthodoxy thinks all this is happening over the ocean in the same way, but we say it's happening over the land. We say it happens because of plants. So now we know roughly the number of plants it takes to produce an average London-style rainfall. But let's take Iquique on the coast of Chile. This is altogether typical. It has prevailing winds from the west, but of course we know now to ignore the prevailing winds. We just count the plants. We draw the line all the way across the world, and there are no plants. It's the Pacific Ocean. There's no possibility of any water vapour. Then the line crosses Australia. What do we know about Australia? Well, it's usually called the desert continent because there's not much there. All right, there's a little bit of sheep pasture over here, but most of Australia, it's just desert. There's no plants there at all. And then the line goes into the Indian Ocean, and there are no plants there. So there's virtually no plants anywhere to the west of Iquique. That's why Iquique gets less than 1 inch of rain a year. 1 inch. It's one of the driest places on Earth. But remember, it's right on the coast. It's right next to the Pacific Ocean. It's got prevailing winds every day coming in off the Pacific Ocean. According to orthodoxy, it should be raining cats. But no, less than 1 inch of rain a year. You can try this for yourself at home. Just take any point on the Earth's surface that gets less than 10 inches of rain a year, draw the line halfway around the world, count the plants. There'll be precious few. Don't choose anywhere in the Ogaden Desert in the Horn of Africa. This is the exception that proves the rule. But anywhere else you wish, less than 10 inches of rain, draw the line, count the plants. If you find very many, especially trees, then this theory is blown out of the water. But if you can't, if this is valid, if the correlation between few plants to the west, little rainfall to the east, turns out to be true, then we have a rule of thumb of great power. Look, geography is not normally an exact science, so we shall have stumbled upon something which by geographical standards is a law of geography. Let's start by returning to our favourite desert, the Atacama, and working out some rules for why it is where it is, and of course why it isn't where it isn't. And then if we've done our work wisely, these rules will also apply to every other desert in the world. Yes, except maybe the Ogaden. Whatever is true for the Atacama will be true for all the other deserts of the world. So this is essentially what we're trying to find out. Why does the desert stop here in the north, virtually on the equator, much further north than orthodoxy says it's decent for a desert to be? Remember the Sahara. Why does it stop here in the east? Even though the latitude hasn't changed, so there ought to be a desert belt all the way across South America. Why does it stop here in the south? In other words, why does the Atacama not obey a single rule of orthodoxy's desert belt theory? Well, let's start with the top and bottom delineations. This is what we might call the general case for all deserts, the default position, or what is known in this theory as the Western effect. Here's the Atacama, here is the Western effect. These are, remember, counting the plants. Have a look at the Atacama Desert as a whole, and you'll see that it obeys our primary rule about having no plants to the west. It's nothing to do with desert belts, it's simply determined by the position of the South American continent at the eastern terminus of the Pacific Ocean, plus the flora of Australia. In the north, we can see very clearly why it stops, because while the Pacific Ocean is common to the whole coastline of South America, on the other side of this ocean, things change. Instead of the barren deserts and scrubby sheep pastures to Australia, there are the rainforests of New Guinea, of Borneo, the Indonesian islands generally. So this is presumptively why the Atacama comes to a halt here in the north, because finally here there is a Western effect, which consists of enough plants to supply enough water vapour to bring the deserts to an end. And now we can inscribe this presumption into our first rule. Any point on the Earth's surface shall be in a desert if the following conditions are satisfied. Rule 1, there are no plants to the west, aka the Western effect. That's the basic rule of distribution of deserts. If the northern limits of the Atacama here are reasonably clear, the eastern limits are even more so. It's clear what ends it, it's the Andes Mountains. The eastern boundary of the Atacama is clearly related to the Andes Mountains. Since the desert occurs nowhere to the east of the Andes, anywhere in South America, but exclusively to the west of them, these are the Argentinian Badlands. They are not true deserts. This peculiar and remarkable mountain range must be providing the deciding factor. Now, I won't go into the reasons at this stage for why north-south mountains end deserts. Let's just assume for now that they do. Because remember, we've got every other desert in the world in order to check whether these claims are true or not. And we can then explore how exactly they work. So for now, along with our rule 1, that there are no plants to the west, aka the Western effect, now we have rule 2. There is no intervening north-south mountain range, aka the north-south effect. Easy to remember, there's rule 1, the Western effect, rule 2 is the north-south effect. In other words, looking at the Atacama, we have the reason why it stops in the north, because the Western effect kicks in. We know why it ends in the east, because the north-south rule kicks in. Now we need to discover why it ends here in the south. So why does the desert end completely in the far south? Now look, this cannot be anything to do with the western effect, which is absolutely nil. The western effect, there is no western effect at all anywhere there. So it can't be the western effect. We know it can't be the north-south effect because, look, the Andes are operating all the way down the South American continent. So it can have nothing to do with the Andes. It cannot be the north-south effect. If it can't be the western effect, it can't be the north-south effect, it must be the eastern effect. I know, but it really does turn out that way, because if we look to the east, we find that it is the closeness of the ocean to the east which correlates with the existence of the desert. So looking at this bit where Santiago is, you'll see it's opposite the Plate estuary. In other words, it's where the Atlantic comes surging in and just gets close enough to knock out the desert. The entire South American continent is so narrow that everywhere is within the protection of the Atlantic to the east. So, no more desert. Now, look, I accept this is a very strange phenomenon, and you'll be quite rightly be sceptical, but once again, you must still your doubts by bearing in mind that this whole notion will collapse if the next desert we look at breaks the rule, or the one after that, or the one after that. If they don't, we can turn to why, we can turn to how the phenomenon operates. But for now, we have our three rules. We have rule 1, there are no plants to the west, the western effect. Rule 2, there is no intervening north-south mountain range, the north-south effect. And rule 3, there is no nearby ocean to the east, aka the eastern effect. And that's it. It's highly memorable, the new theory of deserts. Deserts always exist anywhere in the Earth's surface as long as 3 simple conditions apply. So now, with these very simple rules, we'll have a look at all the other deserts and see if they conform. And remember, they must conform exactly. We're doing the overthrowing of the existing paradigm. So we're not allowed to make excuses. We're not allowed to use special pleading, claim there's local conditions. Actually, we might occasionally do a bit of finagling, but we'll always point these out, and you'll be able to judge whether it blows our model out of the water or not. So, apart from the Ogaden, we shall make this claim without equivocation. Every single desert in the world has to conform to our 3 simple rules. Now, let's take the deserts of the southern hemisphere and see if they all pass the test. Of course, the Atacama gets a tick because we devised the rule specifically with the Atacama in mind. So there's no significance whatsoever in the Atacama obeying our 3 rules. But now let's move to Africa, below the equator, that is, because we're doing the southern hemisphere, and we'll see whether Africa obeys our 3 rules. If we have a look at the map, the simplest way to see how the rules act is first to draw a line parallel to the Indian Ocean, because remember, the eastern effect says you cannot have deserts within a certain distance of the Eastern Ocean. So there cannot be any deserts to the east of that line. Now, the western effect here is rather interesting, because if we look at the western effect for southern Africa as a whole, we'll see that it consists of 3 things. The Atlantic Ocean, where there are no plants, the Pacific Ocean, where there are no plants, and in between the South American continent, where there are certainly plants. So the whole of Africa below the equator relies solely on South America for its western effect. However, let's look at South America. We can see a marked change north to south. In the north, we have rainforest, practically the whole way across. South of that line, the continent is, well, for a start, it's much narrower, so there's going to be less western effect anyway, but it's all pampas, or it's badlands, or it's Atacama Desert. There's nothing much there at all. Now, we haven't quantified this, but we've selected this line. Of course, we don't quite know where the western effect stops in terms of preventing deserts, but we can draw a line somewhere along there and say, well, it's reasonable to suppose that the western effect operates somewhere to the north, but it stops operating somewhere to the south. Now, it's true, we chose this line knowing where the desert was, I grant you that. But you can see for yourself that this is not an unjustifiable claim. So, the deserts cannot occur north of this line, and they cannot occur to the east of the black line, and that means that we have this triangle, which is the only place in the whole of southern Africa where deserts can operate. Do we have any north-south mountains? Well, there is the Great Escarpment, which is a north-south mountain range of sorts, but it's not very high and it's not entirely continuous. So we might say that we can ignore that, but it might complicate the question. So what is the condition? Let's have a look at the deserts, and here we have the Kalahari as predicted. This is sort of full desert and this is a partial desert. We can see that the Kalahari conforms pretty well to our three rules. And notice that nowhere else in Africa south of the equator, nowhere else can possibly be desert. Not because it's near the equator, not because it's in the savanna belt or any other belt, or indeed for any other reason, except that the three rules dictate it. We can definitely tick Southern Africa as conforming with our three rules. And remember, it doesn't conform with orthodoxies. Now, Australia is often, as I said before, it's referred to as the desert continent. And the overall reason for this becomes obvious when we skip all the orthodox explanations, which are remarkably jumbled even by orthodoxies' multi-stranded habits, and simply deal with Australia's western effect. Apart from the north, there is no western effect because to the west are four geographical features. One, the Indian Ocean. Two, a slice of Africa, which is either desert or scrub grassland belt. Three, the Atlantic Ocean. And four, that part of South America that's both narrow and pampas or worse. That's basically why Australia is the desert continent. However, we can now start breaking it down because Australia is not entirely desert. If you look at the north of Australia, you can see it gets the benefit of the rainforests of Madagascar and Congo. Indeed, it gets a bit of the Amazon rainforest as well. It's a long way away from these plants, but we might expect northern Australia to be covered by this western effect. Actually, this is sort of largely masked by Australia's peculiar geography. Here, for instance, is the main eastern effect, which operates like this. Remember, anything within reach of the Eastern Ocean will be saved from desert. So we have this line running parallel to the coast, so we know that there can't be any desert to the east of that line. If we move on and we have a look at the north, the eastern effect, because of the peculiarity of the coast, the Gulf of Carpentaria, the eastern effect affects all these zones. But these are also affected by the western effect from Africa and South American rainforests. So we can be sure there'll be no deserts sort of north of these lines. Now, if we look at the southwest, here we have the Great Australian Bight. a very peculiar geographical feature, but it means that it has an eastern effect which covers the whole of this corner of Australia. That's Perth and Fremantle, Kalgoorlie, places like that, which are dry, but they're not deserts. But in fact, what happens is, because the Great Australian Bight is so peculiarly shaped, it means that the plants here, which have been created by the eastern effect of the bight, now create a western effect which saves Adelaide from the desert. Rather a neat system. You can see that there's enough plants to create a western effect on the other side of the bight. Now, if we have a look at the next map, we can see Australia's rainfall as a whole, and it's very, very striking. I mean, here, look, is the eastern effect, just completely mirroring the coast, and then we have the whole of the north, a combination of eastern and western effects, and we have this zone, and it doesn't quite match up, I have to admit, but it's pretty striking, pretty striking. We can, I think you'll agree that we can tick Australia and Africa and South America. But now, of course, we come to the really tricky one. We come to Antarctica. Now, what's interesting about Antarctica is that orthodoxy sort of regards it as a completely special case and comes up with various explanations for why it's a desert. It doesn't even attempt to come up with a particular explanation, because remember that the whole of, virtually the whole of Antarctica is a howling desert. Almost no rain or snow falls anywhere. It looks very wet, but that's because for thousands of years, millions of years, whatever has fallen has never melted, so it just stays there. But our model, we're not allowed any special pleading. To us, Antarctica is just an ordinary continent, no different from anywhere else. It's subject to our three rules. And we can certainly see the basic reason why Antarctica is more or less all desert. Look, we'll take a point A, this can be anywhere on Antarctica, and we draw the line halfway around the world. Of course, it's not very far in the case of Antarctica, but wherever you draw the line, you'll see that there are just no plants. Whether it's over the land, over the sea, over the pack ice, no plants in or around Antarctica. So there can be no western effect anywhere in Antarctica. And there are no north-south mountain ranges either. So we're left completely in the hands of the eastern effect. You'll see, if we take the same point A, that because Antarctica is circular around the pole, the eastern effect hardly ever reaches the ocean. Wherever you place it, the eastern effect will not reach the ocean, so there won't be any eastern effect. This applies to more or less the whole of the continent. However, there are some very small areas on the coast of Antarctica which do have an eastern effect. And those areas, say here or here, these do have more than 10 inches of rain, or snow equivalent. However, there is one area of Antarctica which most definitely has an eastern effect, and that's here, the so-called Antarctic Peninsula. Remember, the Antarctic Peninsula has no western effect, but it does have a very large eastern effect. It's in fact the only large area of Antarctica which has an eastern effect. And that is why the Antarctic Peninsula has plenty of precipitation. So we can see that Antarctica as a whole absolutely obeys our rules. And we can emphatically tick Antarctica. And that completes our story of the Southern Hemisphere. So let's move to the north. Here we have a rather more complicated situation. because the continents are they're not quite so conveniently laid out in discrete areas, which makes desert prediction inherently more difficult. But that just means the three rules have got to work harder. Let's start with North America. As usual, the most important rule is the Western effect. So let's have a look at the general situation of North America and its Western effect. Well, clearly, the whole of North America is dominated to the west by the Pacific Ocean, which, remember, has no plants. So it doesn't provide any rainfall. Curiously, the Pacific narrows all the way up. As you go further north, the Pacific gets narrower. So it means that down here in the south, it extends virtually halfway around the world. So we can say that places like Mexico and Central America, they have no Western effect whatsoever. It's the whole of the Pacific. This is half the circumference of the Earth. So it doesn't matter that these are rainforests, it's just too far away. But as we move north, we can see that the Pacific is not only narrowing, but it's bringing Asia more and more into the picture. And we know plenty about Asia. Asia is an absolute reservoir of plants. If we look here, where Asia has got close enough to North America to start affecting it by the Western effect, we can see down here, it's perhaps we can say, well, all right, it's paddy fields, and but look, there's plenty of trees, there's plenty of forests, especially up here, and well, the whole of Asia is a fantastic source of plants, of water vapour. Now, remember, we have never been able to quantify the Western effect. So we cannot quantify where it kicks in. And again, you may be perfectly sure that we have chosen somewhere which suits our model. That's fair enough, you can argue that. But you'll also see that it's a perfectly rational line to adopt. We've chosen this line here because below this, the Western effect, there isn't one. Above this line, it's considerable. Below this red line, there can be deserts. Above this red line, there can't be deserts. That is the condition of North America in general, according to the Western effect. But now, let's turn to the Eastern effect. We know what to do. We draw our normal line parallel to the east coast, and we can say that no deserts can appear to the east of that line because of the Eastern effect. And notice now, although this area had no Western effect, now it's completely covered by the Eastern effect. So now let's combine the two, and we can say that there'll be no deserts up here, there'll be no deserts here. So deserts are entirely predicted in this quadrant. Let's have a look at this little triangle where deserts are predicted and see how the north-south effect operates. You'll remember that the Andes were very high and very continuous, and they stopped the deserts just absolutely one fell swoop. But the Rockies, they're not like that. First of all, they're not as high, and secondly, they're not continuous. They tend to be in sort of different groupings. Now, we haven't discussed how the north-south effect works, but there's no need to worry about that at the moment. All we can say is that eventually the sort of combined effect of the Rocky Mountains will, in combination, stop the deserts. But it also has to be remembered that deserts might be interspersed by non-desert areas by the local north-south action of a particular group of mountains. And actually there's a third consideration which we haven't talked about, but it does become increasingly important, and that is modern irrigation works. Remember, if you start building huge irrigation works, you're going to create a Western effect. But also, if you're going to start building transport routes through the mountains, you might start advancing the desert through. Anyway, this process will be it'll be more easily understood when we work out exactly how the north-south effect operates. But in any case, we have, with fair precision, I think you'll agree, we predicted not only where North American deserts occur, but more significantly, why they don't occur more extensively. So we can definitely tick North America. But look, just a small anecdote to illustrate some of these thoughts. In the late 19th century, they were building the Panama Canal, and the engineers, they were worried about the absolutely stupendous amounts of water that would be needed to fill the giant locks when moving ocean-going ships from one side to the other. But they did their measurements, and and they looked at the rainfall figures and consulted all the records, and they decided there was so much rain in this part of Central America that they would never run short of water for the Panama Canal. So they went ahead and built the canal, and for strategic reasons, they cut down the forest either side of the canal for at least 20 miles. Then, when the canal was opened in 1914, lo and behold, they discovered there wasn't enough water after all. And in fact, the Panama Canal has been plagued by a shortage of water ever since. The engineers, they turned to the climatologists, I mean, in rather exasperation, said, well, hang about, why didn't you tell us about this problem? And the climatologists, well, look, it wasn't our fault. When we were doing the figures, we were just unlucky, and it happened to be a period of particularly wet weather, quite unusual. And the normal rainfall is what we get now. Sorry, but it's not our fault. It's just an aberration of the weather statistics. Now, we know the real reason they got it wrong. The climatologists didn't get it wrong at all. The engineers cut down the Panama Canal's own local western effect. They still got the eastern effect, of course, that rainfall is just about saved Panama Canal's bacon. Let's move on to Africa. That is the northern part of Africa above the equator. I'm going to have a look at why the Sahara is where it is. And it's quite obvious why it is once you see the western effect of this entire area of the world. It's completely dictated by the Americas. All this area here, it's got the Atlantic Ocean, no plants, it's got the Pacific Ocean, no plants, so it's got to rely totally on the Americas. And at one point, and at only one point, the Americas disappear. And that is right where the Sahara Desert is. Here's the Sahara Desert. This is the western effect, and you'll see that in between there is nothing. And remember, not just there's very little land, but where there is land, this is mostly desert and scrub. That is why the Sahara Desert is where it's at. It's got nothing to do with desert belts. It's wholly to do with the geography of the Americas. Now, there are no north-south mountains to stop the desert rolling right across Africa. Now, I did promise you that there'd be no exceptions, but unfortunately we do now meet an exception, which is that if you notice, the Red Sea, it ought to stop the desert, it ought to introduce an eastern effect. And similarly, the Gulf here should stop the desert. And neither of them do. Now, I won't go into the actual causes here, but you'll probably be able to guess what they are from this picture. Here you'll see the Red Sea and the Gulf, they're completely obliterated by sandstorms because the Sahara Desert is the biggest desert in the world, it's the biggest source of sand in the world, and you will be discovering in due time that sand is an absolutely essential part of the world system, especially as it applies to deserts. But look, just to get all our special pleadings done here together, here is the famous Ogaden Desert down here, and you'll see it's got an absolutely wonderful western effect, and it's got an eastern effect. I mean, it just shouldn't be there, and I'm afraid that I cannot explain it, and I will not be explaining it. However, here's an interesting, if we have a look at our next map, here's a very interesting position of the political boundaries. Now, in both these areas, the rainfall statistics, they're a bit suspect. They're rather political. But if you have a look at the administrative and political boundaries laid down by the 19th century colonial administrators after the First World War, you will see for some reason they follow the Eastern effect unconsciously. And I think we can assume, since these guys, they drew boundaries for very specific reasons, we can assume that the Eastern effect has somehow differentiated Oman, Yemen from Saudi Arabia, and similarly Somalia from Ethiopia. Presumably the administrators were sort of literally drawing a line in the sand. However, while these are major quibbles, I grant you, the fact is that the Sahara as a whole was predicted by a very striking Western effect. And it means, even if you grant us our exceptions, that we can tick Africa north of the equator as holding to our three principles. And so we come to our largest, and in some respects our most vexatious continent, Eurasia. We can show the Eastern effect. This works quite easily. And you can see why the long stretch of deserts, pure deserts and semi-deserts, they're finally brought to an end by the Bay of Bengal. But in general, Eurasia, as a whole, it's not a desert because of its Western effect. And we can have a look at this because here is the whole of North America. And North America saves Europe from having any deserts whatsoever. And of course, Europe plus North America means that all this has loads and loads of Western effect and that there won't be any deserts up here. North America is full of plants, which means that Europe is full of plants, which means that Asia is full of plants. That's why there are no deserts at these latitudes. But we now come to the Gobi Desert. What's the story? Well, the Gobi is the only desert in the world that doesn't have an ocean at its western edge. On the other hand, the Gobi is the only desert in the world that has on its western edge the world's largest inland sea, the Caspian. Surely it can't be a coincidence. In fact, if we have a look at the Gobi Desert and we have a look at its western effect, we can see that it largely consists not just of Atlantic Ocean, but of Mediterranean, of Black Sea and Caspian. Now, look, I agree, this is stretching things to their uttermost, because normally we would regard that as providing enough Western effect to save this area from desert. So you'll have to accept that. But I think the causal link is not quite broken. And of course, the Gobi Desert is finally ended by the eastern effect of the Pacific Ocean. The wider point about Eurasia is that the three principles explain why deserts only occur in two distinct bands, here and down here, and why the rest of the world's largest landmass is completely free of desert. I won't be dealing here with the minor technical deserts that occur right up in the far north of Siberia, as well as Greenland and northern Canada. But look, since we've scored reasonably successfully with where the Asian deserts are, and more crucially, the vast areas where they're not, we can just about award ourselves one last tick. Now, although I admit there are one or two reservations, we would have to, any fair-minded person would have to say that our great tour d'horizon of the world's deserts, it's been a remarkable success, especially by the a general notion of geographical laws. Our three simple rules, they predicted how deserts are distributed in the world with, 95% success rate? Certainly, we can say that we've established more than a prima facie case. We might claim to elevate a working model to a full-blown theory if we can address some remaining issues. We need to know how the Western effect operates and why the north-south effect stops the Western effect. We need to know how the Eastern effect operates. And this is very critical. How is water lost to the system? Remember, lots of rain falls directly on the ocean. It doesn't go anywhere near plants, and some of it goes off by a river. We have to account for how this is drawn back into the system. So let's move on to number one, how the Western effect operates, because we've kind of grasped this. Here's A. Let's think of A as sort of somewhere in Canada. We're talking about an absolutely direct effect along a line of latitude. Let's say here, this is London. Because it goes direct from west to east along a very particular line of latitude, it cannot be anything to do with just general weather systems, so prevailing winds, that sort of thing. We have to take some factor which is causing it to run along very, very straight lines. And there's only one explanation, it's the turning of the Earth. We must assume that the turning of the Earth is throwing the water vapour that's being generated in the west, and the turning of the Earth then brings it over London or wherever the rain is going to drop. Now, we think that's how the Western effect operates. It needs work. I agree, it needs work, but that's how we think it does. The north-south effect is, well, to understand the north-south effect, we're going to have to go into some very basic biology, and we're going to start overturning one of the life science's most cherished assumptions, and that is this notion that plants are so ingenious, they're so determined, they're so brilliantly adapted that they'll occupy any available eco-niche that becomes available. It's just not true. We can see that it's not true because this shows you that actually plants are utterly hopeless at occupying the Earth's surface. All these areas in pink are where they haven't managed it. And remember, they've had thousands of millions of years in order to occupy anywhere they like. They've had all that time to develop whatever systems they require, colonize wherever they want, develop whatever adaptations they need. But if we look at this map, we discover that the overwhelming majority of the Earth's surface doesn't have any plants on it at all. They haven't been able to occupy the surface of the ocean. Now, you probably never thought about this, but if you do think about it, the surface of the ocean is an absolutely perfect place for plants. They have all the water they need, they have all the sunshine they need, and they can extract all the nutrients they need from seawater, which is a treasure trove of trace elements. Yet plants just simply haven't managed to do it. I mean, look, the Sargasso Sea suggests what they could do if they put their mind to it, but other than that, they've made a right pig's ear out of the job. And it's the same story when we look at the poles. The whole of Antarctica, northern Canada, Siberia, tops of mountains, Greenland, they've got no plants except the odd lichen. Now, people say, oh dear, it's too cold for poor little things. But that's utter rubbish. With all this time on Earth, it should be no bother developing systems to cope with cold. Lots of animals have acquired antifreeze. Why haven't plants? And actually, the Antarctic is not particularly cold. Yeah, it's cold to us, but 0 degrees, minus 30 degrees, it's nothing. Absolute zero is, what is it, minus 200 and something? The idea that plants can't manage in Antarctica is ridiculous. Shame on you, plants. And look, it's the same story with the deserts. Deserts really are a perfect growing medium. They have all that sunshine, they have all the earth they need from the sand. Water is quite often available in aquifers just below the surface. You'd think by now that they'd have twigged how to just send their roots down far enough to reach it. They've had zillions of years to evolve longer and longer roots. It's a perfect test bed for evolutionary adaptation, a la giraffes, the giraffe's neck. So why haven't they done it? How far have they got with their roots? A few feet. It's pathetic. Actually, it's more than pathetic. It must be design. Now, look, I won't go into Gaia theory, partly because it's sort of controversial, but mostly because it's somebody else's theory. But the answer to this sort of plant-averse business must be because the Earth requires huge areas to be plant-free in order for Earth, to survive and flourish. In other words, the internal systems of the world require plants to be there and there and there, but not there, there and there. Since it's apparently so important that the Earth has these areas of nil plants, let's see what they have in common, these areas of no plants. Well, what does the surface of the ocean, Antarctica and deserts have in common? The answer is they've all got shifting surfaces. The surface of the sea is constantly on the move. In Antarctica, snow and ice is constantly being blown over the surface. And in the desert, it's sand or similarly small particles that are constantly changing the surface. So for some reason, and it's baffling to me, but presumably not to Gaia, plants have never acquired the ability to grow in mediums that shift about. Perhaps that I should better state that as they haven't been allowed to develop such abilities. But however you look at it, it does appear that plants require stability. It seems very odd, but nevertheless, it seems to be true. But why? Why, for instance, does Earth require deserts? Let's take the daddy of all the deserts, the Sahara. What does it contain? As we said before, it can be looked at as a giant store of sand. But what use is a giant store of sand? Well, here's a couple of thoughts. It's been argued by orthodoxy, but I'll accept it, that the Brazilian rainforest can only exist because huge quantities of sand are blown across from the Sahara Desert, and they mix with the very poor soils of the rainforest and thus allow the rainforest to keep going. In other words, rainforest might be required in one place, but it can't survive on its own. It requires a desert in some other place. Another theory claims that wind-blown sand is absolutely essential for plankton. And plankton, in turn, is required for the general health of the ocean. It's another theory. It seems reasonable to me. So then we might provisionally assume that these areas of no plants are there for very special purposes, crucial purposes for the well-being of the planet. Just because we humans have no direct use for them doesn't mean that the Earth has no use for them. In fact, we can more or less assume that they're vital and we mustn't mess with them. There must be a reason why Earth is 70, 80, 90% plant-free. So, look, just because we now have the ability to green the deserts, now we know the cause of them, doesn't mean we should do so. It's easy enough to cry, save the rainforest, but how many people are going to get behind, don't green the badlands? So, look, deserts are hugely important, and we should start to think about how they come about. How does the Earth make sure that, for example, there's a Sahara Desert for it to mine sand from? How does it arrange for the hydrological cycle, the new model hydrological cycle? How does it ensure that rain is absent from large areas of the Earth? Well, let's think for a moment about the natural cycle of sand. Actually, that is a paradigm theory, but one that orthodoxy does not pay much attention to. Where, for instance, does the sand in the Sahara Desert come from? Orthodoxy is always a bit cagey on this subject because they don't think it through. They're prisoners of uniformitarianism. They think vaguely that sand is probably eroded desert rock. But there's only one place where sand is created in enormous quantities, and that's at the seashore. This is where huge erosive forces of the surf, the ocean, the currents batter the land over sufficient time and over a sufficient lateral distance to create huge amounts of sand. And this process has been going on for thousands of millions of years. So the question is, why aren't we knee-deep in sand? Where does all this sand go? Well, in short, there has to be a sand cycle. And, surprise, surprise, the Western effect is critical to it. Now, here's sand being created in unstoppable quantities here at the seashore. Since winds are prevailing westerly everywhere, the sand being formed at the western margins of the continents is blown inland, and there's nothing to stop it. That sand will blow and blow and blow, for example, all the way across North Africa, and it will carry on blowing. It will carry on being produced back there on the Moroccan coast, the great surf crashing onto the beach in Morocco. For millions of years, that sand has been blowing across whatever is inland. But it could be stopped. And surprisingly, it can be stopped quite easily. Let's pop across to our own west coast here in Britain. Let's say Cardigan Bay or the beaches of Cornwall. And ask the key question. Well, again, this sand is being constantly created, so why isn't Britain covered in sand? And the answer is beneath our feet. Whenever there's rain about, plants grow. And look, a few yards inland, there's samaran grass. It's specially adapted, remember, to withstand salt and spray and sand. And then you'll find reeds and scrub and small trees, again, all specially adapted to the conditions, but no sand. The point is, whenever it rains, that sand is held right at the coastal margin. It doesn't blow inland. Yes, a little bit in certain climatic conditions. On a stormy day you might get a bit, but that's good. Look, the whole of the Thames Basin is clay. If you add a bit of sand, you create loam, and loam is good for plants. So that means more plants. And that in turn generates more western effects, more rain. The no desert regime becomes as unstoppable as the no rain sand regime. So whenever there's rain at the western margin, the sand stops. What happens to it? Well, it gets blown back into the sea and creates continental shelves, and after, well, it's a long story, and I won't go into it now because this will be the subject of a future talk. We're more interested in no rain because that means all desert. Whenever there's no rain at the western margin, nothing can stop the sand. And the beauty of the western effect is that it is negatively self-reinforcing. Once you have desert in the west, that is now the western effect for territory to the east. The process is seemingly unstoppable. Actually, deserts are not necessarily sandy. They can be stony or silty or salty, but sand is the binding force. It's the bit that stops plants growing. But one thing does stop the eastern advance of the sand, a north-south mountain range. So, in the Atacama, for example, sand is constantly being created on the west coast of South America, but it can't get inland. It cannot get over the Andes. So, on the other side of the Andes, there's no sand, and plants will immediately start growing because there's a stable surface. You might think this is a chicken and egg situation because there's no western effect either, but it seems once you have a stable surface, plants will grow, and once they grow, they can provide their own western effect. But this needs a bit of work. All we know for sure is that north-south mountains will stop deserts. with complete finality in the case of the Andes, gradually in the case of the North American Rockies. Now think about that for a moment, because they're broken ranges. They permit sand from the west coast to sort of worm its way through the gaps, rather like the American settlers, but in reverse. Speaking of human activity, the entire situation in the western United States is affected not just by widespread irrigation, which presumably has its western effect, but on the other hand, if you start building interstate highways and railroads through the Rockies, then you might be contributing to sand getting through for the first time, creating dust bowls, creating climate events of all kinds. Of course, one other thing stops deserts in their tracks, and that's the Eastern effect. Now, I have to tell you straight away that basically we don't know how the Eastern effect operates. Hurricanes, typhoons, tropical storms, they go under various names. Now, you've probably noticed that they virtually always travel from east to west. So, despite weather systems characteristically travelling from west to east, hurricanes, typhoons, tropical storms, they're going the other way. And unquestionably, they're being generated because we can see them forming. And then, of course, they're passed westward over the land and dump water in absolutely colossal amounts. Do they actually evaporate this water from the sea? Perhaps so. But this does not negate our idea that under normal circumstances, the atmosphere cannot evaporate water from the ocean. Because, look, after all, hurricanes and so on are not normal circumstances. Since they're overwhelmingly generated in the warmer parts of the world, it's reasonable to suppose that they're generated anywhere where the equilibrium point breaks down. So, for instance, where the sea is warmer than usual, then the equilibrium point breaks down and evaporation takes place. Now, this might explain the Eastern effect, were it not for the very grave objections that there are a great many places that get Eastern effect rain, but there are no hurricanes, including vast areas in the Northern Hemisphere and the Southern Hemisphere, which are too cold for tropical storms and so on. But we can extend the principle by pointing out that the equilibrium level of the ocean can be broken locally by any number of factors. Take here in London. Perhaps the Thames, or for that matter the Rhine, warms up the North Sea sufficiently to overcome the equilibrium. Maybe a tidal surge coming down the North Sea raises its level sufficiently. Perhaps an outpouring of fresh water changes the conditions. I don't know. It's all a bit nebulous, but remember, just because we don't know how it operates doesn't mean it doesn't exist. The overwhelming correlation from deserts around the world seems to indicate that it does. And it becomes an important factor in solving our next problem, how the water lost to the plant system gets back. Now, it must be borne in mind that most of the water that falls as rain falls over the ocean. So it goes nowhere near plants. And then, of course, we know that a proportion of the water falling on land returns to the sea via the rivers rather than via the plants. So we have to get that water back into our hydrological system. And if we have an Eastern effect, it might account for most of that water. If the Eastern effect is not being produced by plants, but being produced by these abnormal areas of evaporation that produce typhoons or their equivalent in the colder climates, then we can explain maybe where that water comes from. But this is not very satisfactory. It needs addressing. Even so, overall, I think you'll agree we've made out a prima facie case that the current explanation for desert distribution is wrong, and that something better is required, something that mirrors the real world. Now, whether that better explanation encompasses our own 3 rules, that we'll have to wait and see. But come on, Earth scientists, don't just sit there. See if you can come up with something better.